to section 7.5. Today we're going to solve initial value problems using Laplace transforms. So back in the beginning of the chapter, we started looking at this circuit and we did each piece separately, but today we're going to complete the circuit on 3 different problems. Then we're going to take a preview of the unit step function. So as you can see here, comments on notation, the first step of every solution should start by taking L of both sides. So let's do that down here. L of y double prime minus 4y prime plus 5y equals L of 4e to the 3t. The second step is to solve for big Y. Step 2, let's compute the Laplace transform on both sides. To compute the Laplace transform of these derivatives, I'm going to need formulas 19 and 20, which you see on the side right here. Just replace big F with big Y. So we're going to get S squared big Y minus 2S minus 7 minus 4, and then use parentheses. We want L of y prime, which is S big Y minus 2, and then we want L of 5y, which is just 5 big Y, and that equals 4 over L of e to the 3t is 1 over s minus 3. Okay, everything with a y in it stays on the left. So big Y factor, we have s squared minus 4s plus 5. Everything without a big Y goes to the other side. So I'm going to get a positive 2s, and then once I distribute this negative 4, I'll have positive 1 on the left, so that becomes negative 1 on the right, and then plus 4 over s minus 3. All right, well, let's get a common denominator. That's 2s minus 1 times s minus 3 plus 4, all over s minus 3. If I multiply that out, I get 2s squared minus 7s plus 7 over s minus 3. Finally, solve for big Y. So up here in the instructions, we should get y equals blah. So now we've got y equals 2s squared minus 7s plus 7, all divided by s minus 3 times s squared minus 4s plus 5, which is irreducible quadratic. Now, that's a partial fraction decomposition that you can do, and I would expect you to be able to do it. That doesn't mean I expect you to have to do it on your homework. So you can use technology to help you out. If we use Symbolab, we can get partial fractions for that expression on the right. And so this is 2 over s minus 3 plus 1 over s squared minus 4s plus 5. Okay, now we're ready for step 3, which is to take L inverse of both sides. So when I take L inverse of big Y, I get little y. So I'll write little y of t just so you're clear that that's a little y. And L inverse of 2 over s minus 3 plus, when I do L inverse on this part, I'm going to have to complete the square, so I'll just do that now. That's 1 over s minus 2 quantity squared plus 1. Okay, so this guy is formula 3, and this guy is going to be formula 8, a equal 2, and b equal 1. So my final answer is little y of t equals 2e to the 3t plus e to the 2t sine of t. And there's our final solution. We could have gotten that using undetermined coefficients, but this was a lot quicker. Okay, let's do another one. Let's start by taking L of both sides. So L of y double prime plus y is equal to L of t squared plus 2. All right, now we're going to compute those Laplace transforms and then solve for big Y. So this gives us s squared big Y minus 4s plus 1 plus big Y is 2 over s cubed plus 2 over s. Okay, and now factor big Y out of the terms on the left, s squared plus 1. So we have big Y times s squared plus 1. And then move non-big Y terms over. So we get 4s minus 1. And then I'm going to combine these guys as a single fraction. So plus, because that's the hint, if I combine, I won't need partial fractions, 2 plus 2s squared over s cubed. Okay, big Y is equal to 4s over s squared plus 1 minus 1 over s squared plus 1 plus factor a 2 out of the numerator. and we get s squared plus 1. And then in the denominator, we have s cubed, and we're dividing by s squared plus 1. So these guys cancel out. So step 3, we're going to take L inverse of both sides. L inverse of big Y is little y. You can write little y, or you can write little y of t. And that's equal to L inverse of 4s over s squared plus 1 minus 1 over s squared plus 1 plus 2 over s cubed. Okay, and that's equal to 4 cos t. You can see I have a little Laplace transform table on the side there, so you can just reference those formulas. 4 cos t minus sine t, and then that's going to be plus t squared. Now in your final solution, I want you to include the y. You can write y of t or y, but your final solution is an equation, so it's got to have a y equals in front. Okay, last initial value problem. You should probably pause the video and see if you can do this on your own. Step 1, L of both sides. L of y squared plus 4y is equal to L of 4t squared minus 4t plus 10. Okay, now let's compute those Laplace transforms. We get s squared big Y, and then 0 s's, so minus 3, and then 4 big Y equals 8 over s cubed minus 4 over s squared plus 10 over s. And I'm just going to combine these as a single fraction before I go any further. That's 8 minus 4s plus 10s squared over s cubed. All right, factor a big Y out, and we get s squared plus 4. And we have to move that 3 to the other side. So 3 plus 8 minus 4s plus 10s squared over s cubed. And again, I'm going to write that as a single fraction. So I multiply the 3 by s cubed over s cubed, and I get 3s cubed plus, I'm going to write things in descending order, 10s squared minus 4s plus 8 all over s cubed. So finally, the last part of step 2, big Y is divide that by s squared plus 4. So all of that is divided by s cubed times s squared plus 4. All right, now I'm going to take L inverse of both sides and use the partial fraction hint. Little y is L inverse of, I'm going to write this expression down using partial fractions. So I'm looking up here, 2 over s cubed, and then I'm going to write this guy as 2 separate fractions because it'll be easier for me to use my table if I do that. So plus 4 over s squared plus 4 minus 2s over s squared plus 4 minus 1 over s squared plus 2 over s. Okay, this guy is formula 2 in your table. This guy is formula 6 with b equal 2. This guy's formula 7 with b equal 2. This guy's number 2, and this guy's number 1. So finally, little y is t squared plus 2 sine 2t minus 2 cos 2t minus t plus 2. There you go. All right, the last thing I'm going to do with you is a preview of the unit step function. The great thing about Laplace transforms is that they work for discontinuous functions, and in real life, a lot of functions are discontinuous. So first of all, here's the definition of the unit step function. It's like an on-off switch. It's 0 if t is less than a, and as soon as you hit a, it becomes 1. And you can rewrite piecewise defined functions using these two formulas. By far the most common one is this one, and you really do need to memorize this. And let's just see why it works. If t is less than a, then this whole term drops out because u of t minus a is 0, and so you're left with f1. Great. And then, let me erase that. If t is greater than a, then this is 1, and so what you end up with is f1 plus f2 minus f1, which is just f2. And that's what you wanted if t was bigger than a. So let's try it out. We're going to write f as a piecewise defined function using open intervals, and then use the unit step function to rewrite it. So f of t is, well, I can see I'm at 0 until I get to t equal 1. So 0 if t is less than 1, and then once I get to 1, it's t squared. So t squared if t is bigger than 1. So my f1 in the formula is 0, my f2 is t squared, and my a is 1. So using the rule above that I said to memorize, f of t can be written like this. f1, which is 0, plus f2 minus f1, t squared minus 0, and you do need the parentheses, u of t minus 1. Let's clean that up. F of t is just t squared times u of t minus 1. And that works. If t is less than 1, f is 0. And if t is bigger than 1, f is t squared. And we'll work more with this in class and in the next lecture. And that's the end of this section.